Hi, everyone. This is Akshay here. Bhaskar, can you see/hear me?
We can hear you and see you.
We can hear you, and now we can see you.
Excellent. Hi, everyone. So we will be starting the session in about 5 minutes. But I just thought I will join in before to kind of identify the speakers and just be sure things are all okay, if that sounds fine. So I guess the first talk, the speaker is David, right? Wait,
yeah.
Yeah. Okay. So already, David. So you're all good.
Yeah.
Assume. Okay. Bhaskar, do we need to test the presentation mode, or this is fine? You've already done the needful.
Maybe I can test quickly.
You're all good. Yeah, please go ahead and just join us. We have 4 minutes, so yeah, that'll be good. In the meantime, I guess the speaker would be Oscar. Is Oscar here? Oscar Darwin? Not yet. I do not see Oscar Darwin yet.
So the screen looks good?
Yeah.
Okay.
Excellent. Yeah, David, we are all good. Thanks a lot. Does someone else, is one of the other speakers there, I guess, Yang? And the last talk is by Suman. Suman is also not here yet. So I guess we will wait for these people. So yeah, excellent. Hi, Suman. I see that you've just joined. Do you want to kind of, we have about 3 minutes to start. Do you want to try loading your slides to check that the presentation looks okay? Suman?
Sorry, I missed my name first, so I didn't know that.
No problem. Do you want to just connect to check
Yeah,
whether your slides are showing up? Yeah, thanks.
Yes, can you see?
Not. Oh, excellent.
Okay.
Looks good. Thanks.
Okay.
Yeah, that looks fine.
How do I
Okay.
stop sharing?
Stop. Yeah.
Yeah.
Okay. So the others we will do on the fly. Should be fine. Yeah, we have about 2 minutes left to start. So maybe I can request David, you can keep your slides on so that people know that the session is about to begin. But we will start exactly at 2 o'clock. That's fine. All right, shall we start? It's 2 o'clock now. Okay. Hi, everyone. Welcome to the session B5. I'm the chair Akshay, and we have a list of 4 excellent talks in this online version of FSTTCS. The first talk will be on dynamical systems with rounding, and I think the list of authors is too long for me to read within 15 minutes, but I will just say that David will be giving the talk, and I will let him take on. David, all yours.
Thank you. Yeah, so this is joint work with the Technical University of Dresden, the Max Planck Institute for Software Systems, and Anne-Marie Pooley from IRIF. So we're going to look at the dynamical systems reachability problem, but what we do different is we introduce rounding into the system. So what is a dynamical system? Well, you start with a point in space, a vector, and you create an orbit by applying a given matrix repeatedly to the points, and this creates a sequence of points. So what's this matrix doing? Well, it's the product of a rotation matrix and a scalar matrix. So you have scaling 1.15 in one dimension and 1.05 in the other dimension, and a rotation about the center point by some angle. And the effect of this is to produce a spiral which is expanding outwards. So this is a typical behavior of a dynamical system, although of course there are many more behaviors you can get. And our question is, given a particular point in space, does this orbit ever hit this point? So we have this point y here, and we want to know, is this orbit going to hit this point? So as we come past this point, as we simulate the dynamical systems, we see we've missed the point. And since we're an expanding spiral, clearly we're not going to come back and hit this point again in the future. So this is the classical reachability problem. This is the problem we want to study, and it was solved in 1986, and it's in polynomial time. So why might you want to do this? Well, dynamical systems can be used to simulate programming, small computer programs, particularly where you have linear updates in some kind of while loop. And why might we ask the reachability problem? Well, for example, we would be asking, is this guard condition ever met? And so in this case, the guard condition is never met, and therefore this program does not terminate. What we do differently is introduce a rounding function. So we simulate our first point as we would, but then we round in some way. So here, let's assume we round to the nearest grid point to fix the precision of our numerical representations. So if you've got a finite precision allowed, then you'll at each step need to recover back into the precision allowed. So if we now apply our matrix, our updates, we'll get to another point, and then we round, another point and round, another point and round. And you see we start to diverge from the original orbit. And now we can ask the same question, are we going to hit the target Y? And in fact, this orbit does hit the target Y. So having this different orbit, having this rounding embedded into the dynamical system changes the reachability question. And so if you were simulating that program we previously saw with this rounding scheme, the program would in fact terminate. And you see, the further we go, the further we are diverging. So it's not the case that we're rounding each of the points individually. We are creating an entirely new orbit. So this is the problem we want to study. Given a point to start from, a linear update map, a rounding function, and a target, do we hit it? So what do we mean by rounding? Well, the two obvious rounding functions in computer science are given a number, take the floor or take the ceiling. There's also nearest rounding, where, for example, 2.2 rounds to 2 and 2.7 rounds to 3. but you're going to have to decide what to do with 2.5. However, when you're analyzing dynamical systems, you'll often need complex numbers. So to do this, we need to define how you round complex numbers. So one way is to have imaginary rounding, to use a real and imaginary part, and to round each of those parts separately. So you round A and you round B, and this essentially in the complex plane takes you to the nearest grid point. Or you could use the floor function, or you could use the ceiling function, or any rounding function you could think of, but you apply it to each of the parts separately. Another thing you could do is to treat a complex number as a polar coordinate, where you represent the point with an angle and a modulus, and then you round each of those separately. So you round to the nearest modulus and to the nearest angle, and you round to this point. Why do we need to specify this? Well, we'll get different results depending on our which rounding function we use. So we separate our cases into whether we use the polar rounding function, whether we use this argand imaginary and real part rounding, but we only use the floor or the ceiling function, or whether we apply the nearest rounding function. And of course, what we really want to do is to be able to use any rounding function we like, providing it satisfies some sensible property, such as having a bounded effect on the modulus. So that means that most rounding functions will satisfy this. If you round something, it shouldn't move too far from where you started from. So we'll get different results depending on which rounding function we need. Recall, no rounding function is in polynomial time. So for hyperbolic systems, these are systems like in the first example, where you're either expanding or contracting, or formally you have no eigenvalue of modulus 1. Here we show p-space completeness. But if we want to drop the restrictions on the eigenvalues, we don't have such a nice complete result. If the matrix is already in Jordan normal form and we restrict to these two types of rounding, we're in X space. But in particular, the highlight result is that it's still decidable. However, for all of the remaining cases, we do have, we leave the problem open. And in the video, we sort of explain where the key open problem is. So I'll stop there, and I'm happy to take questions.
Right, thanks a lot. We have quite a bit of time left for questions. So, any questions?
I'll ask a question.
Yeah, please go ahead, Shal.
So it seems that the problem becomes considerably harder, rather than I would expect easier than the just Cannon-Lipton version. But so does this carry also to other targets, like half-space targets?
So I have slides on this. So one key difference from the unrounded setting is the bounded polytope. This is kind of easier in the sense that there are only finitely many points, so you just need to ask the same reachability question for all of the finitely many points. But in the unrounded setting, this problem isn't known to be decidable. For the Scullin problem and for the half-space problem, positivity problem, well, these problems are unsolved in the integer case, and therefore if you applied rounding to them, you get exactly the same orbit, and therefore the problem remains equally hard. So we can't solve these targets without solving the unrounded setting.
Okay, thanks.
Prabhat, can you unmute yourself and go ahead?
Yeah. So the rounding is to some nearest precision, right? Like even in polar form, this is rounding is to some nearest like precision digit. But what if we try to instead, like if we want it in the function of epsilons, what is the complexity? Where do they go in terms of the error? In terms of the precision, what is the complexity like? Does it depend linearly on the complexity, or does it?
So we round to a fixed decimal precision. So for example, to 0.01 or to 0.001. So we actually just solve everything for the integer case, and then you could rescale your initial problem. So make everything 10 times bigger or 10 times smaller, so that the precision you want matches the precision we solve the problem for. So we show the complexity for the integer case, but it should just be a pre-processing step to use a different precision. So it shouldn't massively change things.
Okay. Thank you.
Are there any other questions? I have one question. So in your when you do the rounding for complex numbers, you I think round both the real and the complex part, or the in the polar form both these components. So what happens if, for instance, in the normal thing, I round only the real part but let complex part be precise? The reason I ask this is that normal orbit problem is polytime, whereas by looking at the rounded version, you somehow become p-space hard. So is it related to which part that you're rounding? Is that a question?
Not necessarily. So in the sort of trivial case where you don't end up with imaginary numbers, so you start with a rational matrix, you apply a rational matrix, you stay rational. So if you're only rounding the real part and didn't change the imaginary part, it would be the same as, well, you don't have an imaginary part. So the complexity there is going to be the same. It's p-space hard even for rational matrices. So I guess the alternate question would be, what if you only round the imaginary part and not the real part? But then I guess you can sort of trivially trick the problem so that you move the real part into the imaginary, simulate the imaginary part in the real part, and vice versa, and that would be equally hard. By sort of trivially having either the real part or the imaginary part fixed to 0 throughout the system. It's probably not the answer you were looking for, but it would be equally as hard. Yeah.
All right. So what is the source of, I mean, if you could maybe say, what is the source of the, why does this problem, maybe this is related to Shaul's question earlier as well. What is the source of, I mean, the problem going from polytime to p-space because of the rounding? If you could shed some light.
So, so we show p-space hardness by encoding quantified Boolean formula, and the key observation there is that you can essentially encode some logical operations. So for example, if you have a point that can encode, that's either 0 or 1 to represent true or false, and another dimension that's also 0 or 1, you can make a third dimension the and of that or the or of that. And so using the rounding to sort of force you to the true or the false value. And doing this essentially means that there's nothing better that you can do than essentially go through all of the points in some finite region. So certainly if you grow large enough, the system becomes predictable, but in some finite region that sort of means the points are of polynomial size, so there are exponentially many points, you're not going to get any more sort of logic than just simulating through all of those points. Whereas in the unrounded case, you have some predictability even without this.
Yeah, okay. Thanks. Other questions? If not, let's thank David once again. I don't know how this works, so I guess we are supposed to put in the icon for clapping. That's the way it works in this online way, I guess. All right, thanks. Stop sharing screen. We could request the next speaker in. The next speaker is Oscar Darwin. Do we have Oscar Darwin? I do not see Oscar in the list of. So Oscar or Stefan case. Stefan is also not here. Hi. So Bhaskar, what's the protocol on these things?
Maybe we can just go ahead with the next speaker. Yeah.
But then there might be others thinking that they will come in at 2:30 for that talk.
Yeah.
would
I mean,
somebody else in the audience like
if
to
Oscar
address
comes a
the,
bit late, maybe we can have his talk as well, right, within the session.
all right. So you would suggest that I go ahead. I think Key is indeed here, and
Yes.
it's actually these two topics are rather similar. So we can assume that anybody who wants to come for this talk will go for the next one as well. So it's fine. Hi, is Key? Hi, can you? Yeah.
Hi, I'm here.
Hi. So perhaps could you load your slides and be ready? And if Simon does, Oscar does not show up in the next couple of seconds, we will start with your talk. Is that okay?
Yeah, sure.
Okay. Yeah, I still don't see Oscar here. All right. Okay, so let's start with the third talk of the session. And this talk will be given by Ki Tang, and it will be about regulation processes. Okay, you'll have about 12 to 13 minutes. There's questions. 12 minutes. Thanks.
Yeah. So is my slide showing here?
Yes. But you may want to go into presentation mode, I guess.
It's not presentation mode yet?
No, I can see the tools and export PDF and so on. Yeah.
Oh, okay. Just let me try.
Yeah.
So hello everyone. So my paper, I'm going to present my paper comparing labeled Markov decision processes, and this is joint work with Stefan Kiefer at Oxford. So we start with labeled Markov chains. So a labeled Markov chain is consists of a finite set of states, a finite set of labels, and it also has a transition function which maps each state to a distribution of the states, and each state has a label. So there are two equivalence notions of labeled Markov chains. One is called trace equivalence, and we write two probability distributions mu and nu are trace equivalent if and only if the probability assigned to the event, which is all the traces that with the same prefix w, are the same when we start with initial distributions mu or nu. And we have another notion of equivalence relation, which is called probabilistic biassimilation. If two states are probabilistic bisimilar, then these two states have the same labels. And for each probabilistic bisimilation equivalence class E, the probability of transitioning from state S to E is the same as the probability of transitioning from state T to E. And the probabilistic bisimilar denoted by this tilde is the largest probabilistic bisimilation. There are two distance functions that are related to these two previously introduced equivalence notions. The one related to trace equivalence is called total variation distance. Between mu and nu is defined as the maximum probability assigned to the same event for Markov chains begins with initial distributions mu or nu. Then there are several properties of this total variation distances. So for all distributions mu and nu, we have the mu and nu are trace equivalent if and only if the total variation distance is 0. And we also have that mu and nu can be decided in polynomial time. So that also means that the total variation distance 0 can be decided in polynomial time. Then we also have that the total variation distance 1 can be decided in polynomial time. This is a key result by Chen and Kiefer in their LIX paper 2014. The distance, the pseudometric, the distance function related to probabilistic bisimilarity is called probabilistic bisimilarity distances. And it is a function from a pair of states to a number between 0 and 1. And it can be defined as a least fixed point of a function, which I will not introduce here. But there are several properties of this probabilistic bisimilarity distances. So corresponding to, which is very similar to the properties for the trace equivalence, the total variation distances. So we have two states are probabilistic bisimilar if and only if the probabilistic bisimilarity distance is 0. And the probabilistic bisimilarity can be decided in polynomial time, which means that the probabilistic bisimilarity distance 0 can be decided in polynomial time. And we also have that the probabilistic bisimilarity distance 1 can be decided in polytime. So then we have another model, which is called Markov decision processes. And it is similar to labeled Markov chains. But here we have it also has a non-empty finite set of actions. And instead of the transition probability function, now we have a partial function, which maps each state and an action to a distribution of the states. So for each labeled Markov decision processes, we can also define a strategy. A memoryless strategy is a function alpha from the set of from a state to the distribution of the actions. And a memoryless deterministic strategy, we can view this such strategy as a function from a state to a single action, a single available action at a state. So given a memoryless strategy, and here we show labeled Markov decision processes. So the only state here that has multiple, actually 2 actions is Q2. It has M1 and M2 actions. And for given a memoryless strategy alpha and this kind of labeled Markov decision processes and labeled Markov chain and LMC will be induced. So our key result here is motivated by the relationship between the obliviousness and anonymity and the equivalence. We also interested in the problems of equivalence between labeled Markov decision processes. So the problems TV equal to 0 means that is the decision problem whether there is a memoryless strategy for a given MDP such that the total variation distance between 2 initial distributions is 0 in the induced LMC. And the PB is equal to 0 denotes the decision problem that's given the MDP and 2 initial states, whether there is memoryless strategy such that the 2 initial states S and T have probabilistic bisimilarity distance 0. We for these 2 problems, TV equal to 0, we have shown that it is it is extension theory over the reals complete. And the problem is the hardness of the problem is reduced from this NMF non-negative matrix factorization problem. For PB equal to 0, it is the hardness is shown by using the subset sum problem. And we also have polynomial algorithms to decide TV greater than 0, and the polynomial algorithm to decide PB greater than 0. That is, we have shown that there is always a polynomial algorithm to decide whether two initial distributions have total variation distance total variation distance greater than 0, and also a polynomial algorithm to show that the two initial states have probabilistic by similarity distance greater than 0. And we have all the complete results for all the other problems. So except this TV equal to 0, where like we have shown that it is NP hard and it is in XSR, but here a complexity gap remains. So in the paper, we have focused on TV greater than 0 and PB greater than 0 and these two polynomial algorithms. Furthermore, for TV greater than 0, we have not only shown that the polynomial algorithm exists, we have also shown that there's always an MD strategy that we are witnessing this TV greater than 0. But for PB greater than 0, there's not always this MD strategy. So sometimes we need the witness strategy is a memoryless randomized strategy. And thank you. I'm ready to take in any questions.
Yeah, thanks a lot, Ki. Are there any questions? Yeah, Prabhat, please go ahead. You can unmute yourself and ask.
So for TV greater than 0 and PB greater than 0, is it known to be in, like, is it P complete or just in P not? Is there any lower bound known for this?
We have not shown P complete. We have not shown lower bound. We only show the two polynomial algorithms. Yeah, that's a very good question, and yeah, that needs further research.
But even for so this is for MDP, right? So, but even for LMC, I guess it would be P hard. Wouldn't it be equations? I don't know.
So for yes, you're right. So for LMC, this probabilistic by similarity, this to decide the decision problem of probabilistic by similarity, I think it is showing to be P hard. So yeah. So we might be able to use that results to to transfer that results to show that PB greater than 0 for the Markov decision process is also P hard. But is there? I'm not sure if there is also P hard results for trace equivalence.
I don't recall it either. Right. All right. Any other questions? Since one of the speakers is kind of missing, we have time for questions. If not, we will move to the next topic, to the last talk. Right. So there seems to be no other questions. Okay, I have one last question to ask, if I may. So do you think, so this is all on Markov decision processes. What is the link between this and, for instance, could you adapt these results for two classes? One is on Markov chains and the other would be on partially observable Markov decision processes. Could you comment on such things, or are these plans for future work?
So partially observable Markov chains?
Yeah, my Markov
So,
differential. Yeah.
So I know the related work to it is related to this other model, which is called the interval Markov chains, which means the transition is labeled not with probabilities but with probability intervals. So if you so choosing a strategy, so memorize strategy for in MDP will correspond to choosing some probabilities between in this probability intervals. So that might be like some future work. Yeah.
All right. Okay. Thanks, Key. I guess we will move on to the fourth talk in the session, which will be given by Suman. Can you stop sharing your so that? Yeah.
Okay. Thank you.
Thanks. Yeah. Yeah. So let's actually, yeah, it's a bit 1 minute late, but let's thank Key for a nice talk. And let us move on. Yeah, thanks, Shao. Let us move on to the last talk of this session, which will be given by Suman, and it will be on dynamic network congestion games. Suman, you have the usual 12 minutes. Thanks.
Hello everyone, I'm Suman, and today I'll be talking about dynamic network congestion game. And this is a joint work with Nathalie Bathon, Nicola Marque, and Uchan Sankur at MGRN. So several models of congestion games have been studied in the literature. And before introducing the model that we are studying, I'll just walk through a traditional model, which is routing games, and from which we got the motivation from. So this is studied by Ralph Garden, and in this model, you have a directed graph as the game arena, and you have a number of players who are trying to go from a designated source vertex to a target vertex. Now, edges are marked with cost functions, which may depend on the number of players. So for the congestion context, we assume that the cost functions are non-decreasing. And so for example, here the E1 edge is marked by cost function X, meaning that any player who takes that edge E1 in their path have to pay X unit of cost if X many players are taking that edge in their path. So we then we take the sum and compute the individual cost and the total cost. Now, in this congestion context, each player's objective is to go from source to target with some optimal cost. So if you assign some path to these players, they will try to switch their path to reduce its cost if they can. So for example, a red player here would like to switch its path from red to yellow and reduce its cost from 7 to 6. And so would a green player whose previous cost became 8, and now it can switch to reduce its cost to 7. Now, when a player switch its switch its path, other players' cost might get increased, and the total cost might also get increased. So, this behavior of the players is called selfish behavior, because here player only think about themselves. And when some external agent assigns some path, it's shown in the left figure. It's called a centralized behavior. Now, one of the main objective in this area is to study that how this selfish behavior can be can behave compared to the centralized one in terms of total cost. So there might be multiple selfish behavior, and total cost would also vary. So this is more or less the objective in congestion games. And in our model, we differ from the traditional routing games in two aspects. The first one is synchronicity in the cost computation. So in the most of the model, a player bears a congestion effect due to an edge if that edge is taken by the two players in their path. It doesn't matter whether they take that edge simultaneously or not. So in our model, we enforce that condition that two players would bear a congestion effect in some edge if they take that edge simultaneously. For example, here the red and green, all of them will take the edge E4, but the red player is taking the edge at their third step, while the green player is taking at their second step. So they do not bear the congestion cost due to each other. So that reduces the cost somehow, but it doesn't alter any algorithmic question that we study. And another aspect where we differ is we expand the strategy space. So in most of the model in the literature, player are assigned or player takes a path from source to target at the beginning of the game, and they do not change it like in the middle. So what we are considering, a player can observe what other players are playing, and depending on that they can decide what to play next. So for example, here a red player, when they are at state S1, they can see if there are more than two players at S1, they will take the dotted red path, otherwise they will continue the solid one. Now these affect the algorithmic question, and we'll see how. So the problems of interest is first we need to check that whether Nash equilibria exist in our model, and which formalizes the selfish behavior, and the answer is yes. Moreover, it's by showing a termination of a best response procedure. Moreover, we can observe that when we consider a dynamic strategy space from path, we can get some Nash equilibria with some total cost which cannot be achieved if we only consider path Nash equilibria. For example, here if you consider this arena and red players are taking the solid red path, unless if they see that other red player betrays himself or herself, then that red player punish the other red player by taking the punishing edge, that is pun 1 and pun 2. And this is and the green player is taking the path below, green path below, and this strategy profile is a dynamic Nash equilibria with total cost 36. But in this arena, in 3 player, no path Nash equilibria will have total cost less than 37. So this gives us incentive to study the dynamic model, and then we study in this model that given an instance of our model, how well or how bad Nash equilibria behave with respect to social optimum in terms of total cost. Now, wellness is measured by price of stability, which is the ratio of total cost of the best Nash equilibria with the social optimum, and how bad it can behave is measured by price of anarchy, which is the ratio of the total cost of the worst Nash equilibria with the social optimum. Now, to measure, to compute these to measure, we study 3 decision problems. In all of them, the input is instance of our model and a value. And we ask that for the social optimum problem, we ask that whether there exists a strategy profile with total cost less than the given value. For base Nash equilibria, we ask whether there exists a Nash equilibria profile with the total cost less than the value. And worst Nash equilibria, we ask whether all the Nash equilibria profile have total cost less than the given value. Now we solve these 3 problems. For the first problem, we reduce it to a weighted path problem of the configuration graph, and for the other 2 problems, we characterize all the outcomes of Nash equilibria and we develop an algorithm from that characterization by some auxiliary value. And then we compute by binary search the social optimum value, the total cost of base Nash equilibrium, total cost of worst Nash equilibrium, and we compute these 2 measures. Now, the membership of these decision problems are shown here. Now you can observe that there is a exponential blow up when we consider a unique source target pair for all the players compared to when we consider different source target pair. So this blow up happens. So this is there is a blow up in these two decision problem. This blow up happens because when you consider unique source target pair, the number of players can be encoded in binary. So the input size is actually smaller here. So we apply the same algorithm, but there is exponential blow up for when we consider unique source target pair. But for the social optimum problem, we can actually remove this blow up by using a trick in the unique source target pair, but that trick doesn't work for the other two problems. Now, even though we argued that if you consider dynamic strategy profile, you get some better Nash equilibria. Actually, you encounter some bizarre Nash equilibria where you will observe some non-credible threats where player punish other player, but initially the objective was to just go from source to target with an optimal cost. So to get rid of this kind of non-credible threat, the better equilibria in a dynamic context is subgame perfect equilibria, which is Nash equilibria, but not only from the initial subgame, initial configuration, but from all subgame. So that profile is called a subgame perfect equilibria. Unfortunately, the existence of subgame perfect equilibria cannot be, we cannot show in our model, but still we can study the question that I posed for Nash equilibria, that given a game and a value whether there exists a SP profile with the social cost less than the given value. So this problem can be solved in double exponential space, again for same source target pair, and for varying source target pair it is just exponential space. So there is again a exponential blow up, and that's the problem that we study in this paper. And we have some lower bound complexity result for some of the problem like social optimum, but it's not still matched, and for other problem we do not have. So our next goal is to study the lower bounds if we match the lower bound complexity result from the decision problem that we consider. And one of the immediate approach that we are currently considering is that taking the number of players as the parameter of an instance and see how this measure grow with this parameter. And obviously we would like to have a decisive result about the existence of subgame perfect equilibria in our model. So this is open till now. And one of long-term goal could be that to study other than reachability objective like regularity, etc. Thanks.
All right. Thanks very much, Suman. Are there any questions?
I have a question.
Yashal, please go ahead.
How about the problem of looking at the ratio between the best Nash equilibrium and the worst path-based strategies? Have you looked at that? Does it even make sense to look at it?
You mean if you take the ratio of price stability and price of anarchy? Like
no, I mean you said earlier that if you move to dynamic strategies, then you can gain a better social optimum than path-based strategies. So what does the ratio of the best Nash to the paths behave like? Is it even interesting to look at?
What I said is that if you move to dynamic strategy, you might gain in the Nash equilibria. I did not say that you. I mean this. I did not say that you will gain in the social optimum. So, for example, here the total you might get some Nash equilibria with better total cost. So that will improve maybe for this particular example, it improves the price of stability, but it doesn't improve the social optimum because social optimum just strategy profile. So the strategy profile you can observe anywhere. Like this particular strategy profile is also observable if you consider a blind path strategy. You'll just take the path. I mean the outcome of the this strategy as path.
I see. Okay, thanks.
Are there any other questions? I guess not. Let me just ask one question. Regarding in your last slide, you mentioned that you're trying to close the gap between for social optimal between the NP hardness and the P
Yes.
space completeness, P space attainment. What do you expect? I mean, are you trying to show that there will be a hardness, P space hardness, or do you expect indeed something like existential theory of reals, or does that make sense here?
Yeah.
I mean, there are classes in not known to be in between, but
yeah, that I don't know actually, but yeah, I was trying to show that pre-space hardness for social optimum, but I
so what?
not able to, but I might have to look at other classes then.
And for the NP hardness, what problem do you reduce from?
Partition problem.
All right. Are there any other questions? Anyone else? If not, let's. Yeah, no. So let's thank Suman again. Indeed, I'd like it. So I guess our fourth speaker, Oscar and the papers, authors of the paper, I guess are Oscar and Stefan. Neither of them are here. So that will kind of end the session. So maybe can we all unmute and thank once all the speakers as well as rest of you for coming in on a time online. Yeah. Thanks a lot, everyone. And that ends the session. Sunil, if you have something to say.
Next session in about, I think, 45 minutes. Yeah.
A longer coffee break, so please enjoy. All right. Thanks, everyone.
Hello, everybody.
Hello.
So,
Hello.
Hello.
I see Sarah, Shaul, Lina, I think, I heard her, and Praveen. However, I don't see the second speakers, so to say, if you have a network collapse. There were some names, so Emmanuel should be there, and also Stefan Schwan should be there. Should we wait 2 more minutes?
Yeah, right.
Yeah.
To see whether Emmanuel and Stefan appear. So you know how it's planned. So 10 minutes. Yeah, so you were already informed. And so every talk can take up to 12 minutes, and so that we can switch also between talks. So there's no hurry.
Good.
No hurry, so just...
That's what I prefer.
Yeah. Yeah, so I think we should start. So maybe they appear a bit later. So I don't see Emmanuel, but
I don't think Emmanuel is coming.
no, it's just because in case of connectivity issues, he's supposed to replace you, but I don't think that I can contact him just like this in 1 minute.
Yeah, I know, but I remember he told me he is in a PhD defense. So
okay.
Let's just hope everything goes well.
So let's start. So
okay,
please start, Sarah.
Yeah. You see my slides, right?
Yes.
Okay, great. Yeah, this is joint work with Emmanuel Filiot and Christoph Löding. And the talk is about synthesis from weighted specifications with partial domains over finite worlds. Wrong key. Yeah, right key. Okay, so in synthesis, you have a specification where one input can be in relation with several outputs, and the goal is to synthesize an implementation that selects a unique output for each input such that the input-output pair is part of the specification. And here in this talk, the specifications are given by deterministic synchronous weighted automata. What does it mean? It means we have deterministic automata, and on the transition labels, we have a pair of letters, one input letter and one output letter. The upper letter is the input letter and the lower letter is the output letter. For example, this transition means we read input letter A and output letter D. And since it's weighted automata, every transition also has a weight, and here it's integers. And then, the value of a run is determined by the weights that are seen on the run in the automaton, and the value depends what kind of payoff function you use. For example, you could use sum or average or discounted sum, or whatever you like. And then if we take a look at the run for AC, AD, BD, the sum is 3, and AC, AD, BD, this stands for the pair with the input AAB and output CDD. And you can see here in this automaton, in order to reach a finite states, how do the input components have to look like? The input can start with an arbitrary number of A's, and in order to reach this or that finite state, we have to see a B as the last letter. So the specification domain here is an arbitrary number of A's followed by a single B. Okay, and what kind of implementations are we looking for? We are looking for implementations that are realized by sequential synchronous transducers. What are those? Those are basically deterministic automata that on each transition read exactly one input letter and produce exactly one output letter. And if we take a look at this transducer here, this is indeed an implementation of the specification. You can see it has the same domain as our specification, an arbitrary number of A's, and the final state can be reached by reading a B. And for every A, the output is C, and for the letter B, the output is C. And you can see that this corresponds to the left-hand side of the specification automaton. So, okay, here we have an implementation of the specification, but the question is, is this a good specification? Is the quality of this, is this a good implementation? Is the quality of this implementation high or low? And in order to talk about quality of implementations, there are, of course, several ways to define what a good quality, what a high quality implementation is. And some general concepts are that, when we see an implementation as a set of valid executions, that we want to have that all executions have a lower bounded quality, some kind of threshold constraint, or we could ask that all executions are quality optimal, or we could ask, to not be that strict and ask that all executions are almost quality optimal. There are, of course, more ways to define what good quality implementations are, but these are the three concepts we did take a look at. Okay, so I will go into more detail. What does this mean for our specifications given by our weighted automata? It means the first one. In the threshold synthesis problem, we have a threshold and we ask that the implementation satisfies for all valid inputs. Valid means they come from a specification domain, that the value achieved by the input-output pair generated by the specification, that it has to be greater or greater equal to the given threshold. So let's take a look at an example. This is the same specification as seen on the very first slide. Let's interpret it as a sum specification. Then here on the right-hand side, we have this sequential transducer. It is indeed an implementation. For every input letter, the output is D. And you can see here again, the domain is an arbitrary number of A's followed by a single B. Okay, and what does this implementation achieve? This implementation ensures a value of at least 3 for all pairs. So the pair input B with input D, this is value 6. And for all input words that contain at least one A, if we follow the corresponding run in the specification automaton, we see here that it goes into the right-hand side of the automaton, A with output D, possibly more A's with output D, and then finally BD. So the sum of these runs is 3 or higher. Okay, so that's threshold synthesis was one example. Then let's take a look at best value synthesis. Here we ask that the implementation guarantees for an input U that the value that is achieved by the implementation corresponds to the best value achievable for this particular input, and best in this case means it should be the maximal value. So let's take the same specification and take a look at what are the best values. Well, B, it can be combined only with one output D. The value is 6. And as soon as if we have input letters A, we can decide should the output be C or should it be D. Then for AB, the best value is realized by choosing the output CD, which gives 5. For AAB, the best value is 4. This can be realized by 2 different outputs. If we go AC, BD, the value is 4. But also if we choose D as a first output letter for A, we could do AD, BD, and the sum would also be 4. And then as soon as if we have 3 or more A's, the best value is always achieved by producing D's for every A and then also D for the B. Okay, and if you see this automaton, it is pretty clear that there is no best value implementation, because if you read the first A, the implementation must decide, okay, should the output be C or should it be D? And this depends on the number of A's yet to come, which is unknown. So no best value implementation can exist. So this brings us to the last problem we studied, the approximate synthesis problem. Here we want that the difference of the best value and the achieved value by the specification is smaller or smaller equal to a given threshold. Yeah, again, this is the same specification, and here we have yet another implementation. What does it do? For input B, it outputs D, and then if it sees an A, for the first A, the output is C, and for all subsequent A's, the output is D, and then at some point we see a B and combine it with output D. Yeah, and I guess you can see that is, again, it is an implementation. You can combine the first A with C and then all subsequent A's with D by going to the right-hand side of the specification automaton. Okay, so how does it compare to the best value achievables? We have a difference of at most 2. For the pairs BB, the achieved value of the implementation and the best value achievable is equal. Also for AB, the achieved value of the implementation and the best value is the same. But then if we have 2 or more A's, the sum achieved by the implementation, the runs corresponding to the outputs follow this path, 1 times C and the rest D's. So the value of these runs will be I. And if we consider the best sum achievable for these inputs, it would have been achieved by producing directly a D for the first A. So the sum will be 2 higher compared to the value achieved by the implementation. Okay, so these are the problems we studied, and as specification automata, we studied specifications given by synchronous deterministic automata with sum payoff, with average payoff, and with discounted sum payoff. On the left-hand side, you can find the problem descriptions. We considered strict threshold, non-strict threshold, best value, and strict and non-strict approximate synthesis. Yeah, this work is focused on complexities. Some of the results were already known. If we go to the case of discounted sum automata and approximate, then we have no results for the general problem. But if we restrict ourselves to discount factors that are of the form 1 over n, where n is an integer, then we can solve this, and the complexities are next time in the case of strict approximate synthesis and X time for non-strict approximation. Yeah, that's all I have to say. Thank you.
Anka, I think you are on mute.
Sorry. Sorry. So I was saying that what I propose is to take questions after the talk, and in case that there are more questions that you have want to ask later, we can ask also at the end of the session. So let's start now for with the questions to Sarah's talk. Is there anything you want to know from Sarah?
I have a question.
Yes, please, Charles.
What happens for non-deterministic specifications? Is there anything else, like max plus or something like that?
For non-deterministic, this is unclear and we plan to investigate. The only thing we know, if you go to unambiguous specifications, which is in between, then if you consider threshold problems for sum and average, then the problem becomes undecidable.
Other questions? In the audience? You can ask them just by unmuting yourselves. You don't need to raise hands. So I have a small questions about the synchronicity assumption.
Mm-hmm.
So how important is the fact that you output only one letter? I guess it is, because the reduction to games is probably...
Yeah, very. Originally, we started out to also consider some asynchronous stuff, and but it got very complicated fast to fit it all together, like asynchronous specifications with synchronous quality measures, and then it's very hard to combine these in a meaningful way that stuff still gets decidable and you can easily determine what exactly the value is of the implementations you generated, yeah.
So you don't know whether it's undecidable if you take asynchronous specifications or implementations?
For threshold, for example, if you consider asynchronicity where you have a bound of the then you can recover decidability. But if you allow complete asynchronicity, we don't know.
Thank you very much, Sarah. Any other question in the audience? As I said, so if you have more questions, so at the end, we can still ask some questions. Then I would like to ask Lina to unmute herself and to share screen.
Okay, can you hear me?
Yes.
Okay, great. So I'm here. So can you hear? Can you see slides?
Not yet.
Okay. Thanks, Anger. Thanks everyone for being here.
Not yet. So we don't see the slides yet.
All right. But I had to do. And now?
No.
Okay, I begin. For my side version.
Yes, now it's okay.
Okay, it's okay. Okay, great. Thanks. So thanks everyone for being here. So now I talk about the work on active prediction for discrete event systems. So this is joint work with Stefan R. and Sejada Stefan Shu. So first, the study that we study are actually partially observed controllable systems. And for such systems, it's very important to construct the mapping from observations to control actions to guarantee important properties such that system can always stay in a desirable state. And so a little bit about diagnosis prediction. Okay, and for the partially observed system, it's a central task. One central task is to detect or prevent occurrence of some important events called fault events. So two corresponding properties that need to verify during the design stage. Diagnosability is a system property to guarantee that every fault can be diagnosed. So this problem is actually in p-type time, and active diagnosis is to synthesize controller based on observations, such that system can always stay in a subset of its diagnosable behaviors. So this problem is expo time complete. And predictability is also system property to guarantee that every future fault can be predicted before its occurrence, so which means the system still in a normal states. So this problem is also in P time, but active version we don't know. So this work is to get a result for the active predictability. Actually, we prove that it is expo time complete as well. Okay, our model is a classical label transition systems, except that we divide the set of events into a subset of observable and unobservable events. Fault event is unobservable. So we adopt classical two assumptions in the domain, leftness and convergence, which means that from each state system can continue, and we guarantee that there is no infinite sequence of unobservable events. So this is an example of life, of system life and convergent. Okay, we use a dash to represent unobserved event. So I will not here introduce the formal definition about predictability. I just give you a very simple idea with a simple example. For example, here, consider that this is a set of behaviors of a given system, and the blue one observed events, red one fault events, and purple means it is a normal behavior. Okay, I use the R's to represent that two observed events are the same. So for this system, actually, when we observe this sequence of events, this one is the observed event just before this fault occurrence. So when we observe this sequence, there are still two possibilities. One is normal behavior, infinite normal behavior. Another is behavior that will contain fault immediately. So this fault occurrence cannot be predictable. Okay, this system is not predictable. Now let's look at this system. Actually, when we observe these three events, and we are sure that all consistent behavior, consistent with the observations, three possible behavior, that all of them contain the fault. So the fault, every fault can be predictable by excluding this normal behavior. Okay. So for the predictable system situation, actually we can do better. Suppose that we observe these three events, and we are sure that fault will occur between K and K plus L further observations. And if each fault behavior can be predicted in this way, and it is KL predictable, we are happier for this. So the controlled LTS, we adopted the same definition in the paper of R. So a subset of observed events are controllable. So when controller observe a sequence of events, and it can decide which subset of events that are allowed for the next step. And in this way, it restricts the behavior of system. For example, here, when controller observe nothing, empty observation, it decide to forbid the occurrence of A. So from Q0, only B and C are allowed. Actually, this system with this controller, it becomes predictable from non-predictable. And so we define for legal prediction. Top means cannot predict a fault. K error, system currently correct, but fault will necessarily happen between K and K plus L for the observations. And question mark M means fault, either fault has already occurred or fault will necessarily occur within M further observations. And if we are sure about fault occurrence, then we use button. And we also formally define the compatibility between a successive prediction and in a way such that once a prediction window is given, and can only become more precise with one further observations. This property actually can be guaranteed by two rules imposed on the evolution of lower bound and upper bound. And for example, lower bound can only be decreased by 1 at maximum. Upper bound can only be decreased. And in this way, we can only shrink or maintain the prediction window. We cannot enlarge it. We cannot forget it. And we also define active predictor, which is actually a pair of controller and prediction. And controller should always keep the liveness of the system, and prediction need to correspond its semantics, and we need to guarantee the compatibility between successive prediction. So we prove with this definition, we prove the equivalence of KR active predictor, existence of KR active predictor and KR predictability of the corresponding controlled LTS that is live. So a little bit about knowledge that controller need to know. Controller need to memorize two subset normal set and faulty set that are reachable with normal or faulty behaviors consistent with observations. And P is non-deterministically decided by respecting the compatibility that I explained before. So we also define the valid knowledge that need to respect some constraint between the two subsets and the prediction. For example, if the normal set is empty, which means that no faulty behavior possible, so a prediction must be bottom. So for example, for this system, when we in the initial state, and this is initial knowledge, normal set Q0 and faulty set empty because no faulty behavior, and top as prediction. When it observes A, which means that we either enter Q1 or Q4, both are normal states. And so update the normal states Q1, Q4 will keep faulty set, and then prediction need to update it because now we will show that fault will necessarily occur within 0 and 2 further observations. And in our setting, both predictions should be compatible. And how to construct a Bijou game such that it has a positional winning strategy if and only if an active predictor exists. So now let's look at this example. And here, controllable events is ABC, and control, we have two player, control and environment. So at the beginning, control chooses a prediction when for empty observations. Suppose it's here, and it's initial knowledge, and then game repeat 3 steps. First, control restricts a set of possible actions and based on the controllable events, and then environment, it chooses a possible action to continue. Once environment chooses a possible action, then control need to update its knowledge. Okay, so next, control also need restrict the set of possible action, repeat these 3 steps. And actually, one point that I want to say is that we construct this Bijou game in a way such that if faulty cannot be predictable under some control strategy, then in one future moment, either there is no updated knowledge is not valid, or it cannot respect the compatibility between prediction. So in this case, game enters into a lost state and stay there forever. And we need to find other control strategy that may be winning. So in this way, it proves that active predictability problem is expert time complete. So first it belongs to expert time. We prove the equivalence between positional winning strategy and existence of a KR active predictor, and it is expert time hard. This is done by reduction from safety game with imperfect information. And we also prove that this game actually can be solved in linear time, and unlike in general case, it can be solved in polynomial time. So this is done by reduction to reachability and the safety game. So we also have some bound results. For example, for a given LTS with exactly n states, if all faulty behavior can be announced ahead of in advance of 2 to the power of n steps, then we can, it is actively safe, which means that in this situation, we can construct a controller with which the system can always stay in a normal state without fault occurrence. And however, this bound is asymptotically precise because we proved the second theorem. There exists a family of systems whose state size is linear, a number of n, such that they are not active safe, but they are 2 to the power of n active predictable. Okay, several directions for future work. First, we want to quantify the fortunes to find a better active predictor in terms of this criteria, and we want to extend to the notion of pre-diagnosis, which is actually a notion that combines the predictability and the diagnosability. And finally, we want to study the active predictability for probabilistic systems. Okay, thank you for your attention.
Thank you, Lina. Let us take maybe one question, 1 or 2 questions. Is there any question in the audience? Okay, so I have perhaps a question. So I was wondering whether this bound of 2 to the n, I mean, this comes from what actually, the 2 to the n? So
2 to the n actually is a level bound. N is the size of the system states. Yes. And if we prove that we can construct a system, for example, whose size is not n, but a linear number with respect to n, and such that it cannot be actively safe, fault necessary will occur. But it is 2 to the n power active predictable. We have already constructed this system to show that this bound is actually asymptotically precise. Because if
my question was whether this 2 to the n can be lowered if the graph, if the LTS, the underlying graph of the LTS has some properties like I don't know about diameter or stuff like that.
This is the relation between the active and safe. So can you repeat your question? I
was wondering whether there is any graph parameter that could lower this bound of 2 to the n. So how the 2 to the n comes, where it comes from. So
how to say it? 2 to the n.
So if the diameter, for instance, of the graph is smaller, so do you get also the same bound? So on what kind of graph do you get the lower bound?
What kind of graph? This is okay. This is automata, so it directs the graph. Directs the graph, and it is actually it's a very general. For me, it's a graph directed and also cycle. So there's no other constraints on the. It's not a tree. It's not something else.
No, of course, yeah.
Okay, thank you.
Okay, thank you. Any other question from the audience? If not, thank you, Lina, for the talk. And I propose to switch over to Shaul.
Thank you. Let me just share my screen. Okay, can you see the slides?
Yes.
Perfect. Let me just put a timer, so thanks. So this talk is about process symmetry in probabilistic transducers. And before I define what process symmetry is, I need to introduce some things. So I have 3 things, a blue thing, a green thing, and a red thing. And if you want to see the things move and talk and just run about, I suggest you see the video talk. It's much better than listening to me. But since you're here, the things have a bowl of food that they share, and they want to eat their food. And in order for them to get their food somehow fairly, I've placed it behind some arbiter. And this is a round-robin arbiter, and it works like this. Each thing gets onto a platform. So blue thing went onto platform 1, green to platform 2, and red to platform 3. And they can request food in their turn. So in the first turn, the first platform is allowed to ask for food. And if it asks for food, it gets one. And if not, it doesn't. In the second turn, the second platform gets its turn. And in the third platform. So for example, if the blue and green things ask for food on the first turn, and then on the second and third turns, the red thing asks for food, then the arbiter gets to see the inputs platform 1 and 2 on the first step, and then platform 3, and again platform 3, as you can see here. And now the arbiter sees this input and gives food according to the round robin rule, which means that on the first turn, it was platform 1's turn. So platform 1 gets food. And then on the second turn, the second platform didn't ask for food, so it doesn't get any food. So no food is given. And on the third turn, platform 3 asks for food, so it gets food. And the problem is that despite the clever appearance of these things, they are quite stupid. And sometimes they get on the platform on the wrong way or in some other way. But they ask for food with the same strategy. So still, the blue and green things ask for food in the first turn, and then the red thing on the second and third turns. And now the transducer sees the inputs 2, 3, and then 1 and 1. And it doesn't give out any food, because on the first step, platform 1 didn't ask for food, and on the second step, platform 2 didn't ask for food, and on the third step, platform 3 didn't ask for food. So nobody gets any food. And the problem now is that from the point of view of the things, this is not process symmetric. So the things don't care which platforms they get on. They just want to be given the same food, given the same requests. So the question is, can we fix this? Can we somehow make this transducer symmetric? One way to do this is to add probability, to turn this into a probabilistic transducer. So in this case, we choose uniformly at random which process is going to start, so which is going to be given the first turn. And now if we go back to the first order of the things, if they ask for food in this way, what we get is a uniform distribution on the outputs. So we have 3 possible outputs, depending on who goes first. So if player 1 goes first, then we have this output. If the second one goes first, we have this output. And if the third one goes first, we have this output. And now if the things go on in a different order, then we get a different distribution of outputs, but the outputs associated to the correct inputs don't change. So one way to see this is if you look at the colors of the numbers here and disregard the numbers, we have green, red, nothing, and blue, nothing, red. And if the things change their order, we still have green, red, nothing, and blue, nothing, red. So from the point of view of the things, this is process symmetric. Right. So formally, what we look at is probabilistic transducers over an input set and an output set. And the signals in the input set match the signals in the output set. So there is a correspondence between the first input and the first output. And you can think of it as which process asks for food and which process gets food. And a probabilistic transducer has states labeled by outputs. And it reads an input letter. For example, here it reads I1, I2. This is an input letter. And it has some probability of seeing each of these output states. These are the probabilities. Now, if you look at some permutation of the numbers 1 to k, so think of it as a permutation of the inputs or of the outputs, we can permute the signals within an input letter. So for example, the input I1, I3, if we look at the permutation that takes 1 to 2, 2 to 3, and 3 to 1, we can permute this input and get the output I2, I1, because I1 goes to I2 and I3 goes to I1. And now we say that a transducer is process symmetric if for every permutation you take, and for every input word, if you take the transducer and run it on this input word, you get a distribution of output words. If you permute each of these output words, which means you permute each letter within the word, then you get a distribution again of output words, of permuted output words. This would be the same distribution as you would get if you take the transducer and ran it on the permuted inputs. So basically what I'm saying is, if you take a word and you permute it, you will get the same outputs as you would get if you first ran on the original word and then permute the outputs. So you commute with the permutations. So the first natural question to ask is, given a transducer, can we decide whether it's process symmetric? So can we decide whether for every permutation we have this equality? And the first thing we want to observe is that this may sound scary because we need to check this for every permutation. But in fact, process symmetry has a nice property that if the transducer is both pi symmetric and tau symmetric for 2 permutations pi and tau, then it's also symmetric for their composition. So in fact, we only need to check the generators of the permutation group. And the permutation group is generated by 2 permutations, the cycle and transposition. So it's enough basically to check for a process symmetry of 1 permutation. So how can we do that? We have a very simple construction. We take our transducer and we build from it automata. So in this case, we build probabilistic automata in the following way. We basically push the outputs onto the transitions. So here, for example, we start in state as 0, and we read the input letter I1, I2, O1, which corresponds to the transducer reading I1, I2, and hoping that the output is going to be O1. So here, with probability 0.2, we get to state S1. With probability 0.5, we get to state S2, like here. With probability 0.3, we guessed wrong, and the output is not O1, so we go to a rejecting sink. So we end up with this probabilistic automaton, And the property that this probabilistic automaton has is that the probability with which it accepts a word composed of inputs and outputs, so inputs x and outputs y, the probability this is accepted by A is the same probability that the transducer outputs y when reading x. So basically, this automaton captures the transducer in a way. And then we build a second automaton, B, which behaves exactly in the same way, only we permute both the inputs and the outputs. And the property this automaton B has is that the probability with which it accepts the word xy is the same as the probability that the transducer outputs pi of y when reading pi of x. So this captures the permuted transducer. And now the transducer is process symmetric if this automaton is equivalent to this automaton. And equivalence of probabilistic automata can be checked in polynomial time. This is a fairly old result, but it's non-trivial at all. But we can check it, and then we can decide if a transducer is process symmetric. So this is great. But process symmetry is a very restrictive notion. So sometimes we can't guarantee process symmetry. Sometimes we don't even want exact process symmetry. So we propose 4 relaxations of process symmetry, and I will quickly run through them. So the first relaxation, in a standard symmetry, we require that these two probabilities are the same. So the probability of seeing y for input x after permuting the outputs is the same as the probability of seeing y if we run on the permuted inputs. The first relaxation, which is very straightforward, is to ask, instead of these probabilities to be equal, we just ask that the distance between them is no more than delta for some given delta. And it turns out that this is a bad definition in 2 ways. The first way that it's bad is that it's not composable. So if something is delta pi symmetric and delta tau symmetric, it doesn't mean that it's delta pi tau symmetric, because this blowup of delta can occur in each permutation. So it doesn't compose well. But even worse than that is that deciding whether a transducer is delta symmetric is undecidable. So there was no point of that. So further relaxation is to ask, instead of these two probabilities being equal, we just want them to have the same support. So one is greater than 0 if and only if the other is greater than 0. And essentially, this abstracts away the probabilistic nature into a non-deterministic nature. So what we get now is basically the same reduction, but we end up with NFAs instead of probabilistic automata. And then we can show that the problem of deciding whether something is qualitative symmetric is p-space complete. So this is a nice way of relaxing symmetry. Another way is to disregard the order of the outputs. And for that, we look at what I call Parikh symmetry. So here, take an output word. Instead of looking at the output word letter by letter, we just measure how many signals occur in each of the letters of y. And I call this the Parikh image. It's not exactly the Parikh image in the standard definition, but it's the signal Parikh image, if you will. So this is a vector of numbers that measures how many output signals were of each type in y. And then when we run the transducer T on an input word x, we get a distribution of output letters. And from that, we get a distribution of Parikh images. And then we define 2 notions of symmetry. Parikh symmetry in distribution says that for every permutation pi and every input word x, if I take the transducer and I run it on x, and then I look at the Parikh images of these outputs, and I permute the entries of each Parikh image, this would be the same distribution as if I take the permuted word pi of x, take the transducer and run it on that, and then just look at the Parikh images. And another definition is Parikh symmetry in expectation, which asks the same thing, only on the expected Parikh image. I won't go into that because of time constraints. So what we show is that both of these definitions can be checked. Distribution version can be checked in NC, and the expected version can be checked in randomized NC. And this uses probabilistic reward automata. So again, the same reduction basically, but a different model. So to conclude very quickly, symmetry is a design concern which we want to check for many types of protocols, and we propose several notions of process symmetry. And for future work, we want to look at symmetry in several variants. So several variants of the definition of symmetry. As you saw, there are many ways of defining symmetry, but there are also many different models. So we looked at probabilistic transducers, but there are tons of other models that can or cannot be symmetric, and we want to look at that. Thanks. That's it.
Thank you, Shaul. Thank you for the talk, and we have some time now for some questions. Let me see. Is there anyone in the audience who would like to ask Shaul about symmetry in transducers? let me start perhaps. I was wondering whether you can have also partial symmetries, so in the sense that you are taking, I mean, in your examples, you are taking the identities of the processes, and then you have exactly that many input and output signals. But what if you you only consider partial symmetries? So
yeah, certainly. So one way, obviously, is to have some like external variables that don't relate to the processes, which you want to include in the alphabet, and that's easy.
Right.
Proper partial symmetry, so associating sets of inputs with sets of outputs. I haven't looked into that, but my guess is that it would be very possible. So basically, once you can encode this symmetry into automata, then you're good. Once you can construct the automata that are equivalent to each type of symmetry. So symmetry basically is a notion of partial information. So the process don't know which platform they get on. If you can model that, then things are safe. And I think partial symmetry should be captured this way.
Mm-hmm. And are there any decision problems that get easier on if you have symmetric transducers? So something that, for instance, was undecidable in the general case and gets decidable if you get you have as input.
I don't think so, because you can always, especially if you allow partial symmetry, you can always restrict to the case of one permutation only.
Yeah.
I haven't seen any such properties. My guess is no, because once you have you can always take a permutation, and if you permute the input on the first step, you can like build components that correspond to each permutation, and then you can duplicate your problem onto the instances according to which permutation you're on. So it doesn't typically make things easier, but it might make some properties trivial, I suppose. But I haven't seen any examples of that.
So you are talking, for instance, in the full talk about parameterized properties, where you want to check some property for any pair of processes or something alike, and then you can. So here you get a better complexity, right?
Exactly, yeah. So so my argument is actually that process symmetry deserves to be like a standalone thing that you want to have, but it indeed makes some things easier to check. For example, if you want to check that for every process I, if I ask for food before J, then it gets food before J. Then if you have process symmetry, you only need to check this in one example. You don't need to check this for every two processes. So it eliminates some quantifiers in LTL, for example.
Mm-hmm. And could you think about some setting where you don't limit the number of signals, so in order to have
there is a work on that by
framework for parameterized transducers?
So there is a word called there is a work about regular symmetry patterns by Anthony Lin and others from 2016, where they look at these models but in deterministic transducers. And then the problems are slightly different, because then the choice of group really matters. So if you look at the group of all permutations, things are fine. But if you look at the hydraulic group of permutations, then things become harder. It's a different type of question. I haven't looked at parameterized systems yet, but it's certainly interesting.
Okay. Thank you very much.
Thank you.
Are there perhaps other questions in the audience? If not, then I propose to switch over. So then thanks again to Shaul, and to switch to Praveen. Thank you, Shaul.
Can you see my screen?
Yes.
Okay. This work is about a machine-independent characterization for a class of transducers which work on data words. Data words are strings over infinite alphabets. So let me describe the class of transducers that I consider. So that the class I consider is a fragment of something called streaming data string transducers. So I will not give the formal definition, but try to give a intuitive description. So here is an example transduction that I want to achieve. So suppose the input is such that the first and the last data values are equal, then I want the output to be the same as the input. Otherwise, I want the output to be the reverse of the input. So here is a streaming data string transducer that implements this transduction. So before the construction here are a couple of examples. If the input is 1831, the first data value is 1 and the last data value is also 1. So the first and last data values are equal, so the output is same as the input. Whereas if the input is 3456, the first data value is 3 and the last one is 6. So they are unequal, so the output is the reverse of the input. Okay, so this is the transformation that I want to achieve. So here is a SDST that achieves this. So this streaming data stream transducers have memory elements, two kinds of memory elements. One is the registers, which are represented by this small square here, which can store a single data value. And it is both readable and writable. The transducer can read what is there in the register, as well as it can put new data values that is coming from the input into this register. There is another kind of memory element called data word variables, which I represent by extended rectangles here at the bottom. These extended rectangles can store sequences of data words. This sequence can be unbounded in length. I mean, it need not be one data value like it should be in register. So in data word variables, you can have a sequence of data words. But this data word variables are write only. We can write stuff into this, but the transducer cannot make decisions based on what is there in these data word variables. Okay, so these are the memory elements that are there in the transducer. Now using this, we can implement this transaction as follows. So the transducer starts reading its input from left to right. The first data value is 1. So the transducer stores the first data value in the register as well as in the two variables. And then it goes on to read the next data value, which is 8. It stores the next data value. It appends it to the first data word variable. It puts it into the front, while it puts it into the back of the second variable. And then it continues doing this with the incoming data values. 3 is put into the front of the first variable, and it is put into the back of the next one, second variable, and so on. And once the final data value is read, now the transducer can see that the first data value, which is stored in the register, is equal to the last data value, okay, which is just been read. So since the two are equal, the transducer outputs the content of the first data word variable, which is essentially the input. We have just copied the input into the first data word variable. Now what happens for the other example? Again, it reads the first first data value, which is 3. It is stored into the register as well as the two variables. And it continues to read the other data values. And when it sees the last data value, it sees that the first data value, which is 3, which is stored in the register, is different from the last data value 6, which has just been read. So since these two are unequal, the transducer now outputs the value stored in the second variable. And due to the order in which we have been storing the data values, the second data word variable contains the reverse of the input. So it outputs the second data word variable, and that is the output that is needed. So this is roughly the way these streaming data stream transducers work. There are a lot of details that I have not mentioned here due to the lack of time. You can refer to the paper details. So what I consider here is a fragment. So in the original SDSTs that were studied, you could also have a linear order. So here, for example, the last data value being read is 6, and the data value that is stored in the register is 3. The transducer can not only check whether these two are equal, it can also check whether the value stored in the register is less than the value that is being read. It can check whether this 3 is less than 6. So there is a linear order on the data values, on the set of data values, and the transducer can check whether the two data values are related in this linear, how they are related on the linear order. The fragment that I consider in this paper is a fragment where this linear order is not there. Only the equality checking is there. And so that is the model that I call streaming string register transducers. So I chose to give this name because the version of this transducer without data values, the version of the transducer which only deals with finite alphabets, that is referred to as string transducers. And I have just introduced the word register, just like we have register automata. I'm calling it streaming string register transducer. And the goal of this work is to give a machine independent characterization for SSRTs. It turns out that to give this machine independent characterization, first you have to identify what are the data values that need to be remembered by the transducer when reading the input. So here in these two examples, it's kind of intuitive to see that a transducer needs to remember the first data value, because everything depends on whether the first data value is equal or unequal to the last one. So the first data value needs to be remembered. But in general, the question is to precisely mathematically define when is it that a data value needs to be remembered. So here is a more formal question that needs to be answered. For computing the output of a transaction F on an input data word, let's say D1, D2, D3, this is not an infinite data word. I'm only considering finite data words, but I forgot the fact that dot at the end might mean infinite data word, but I'm only considering finite data word. So suppose you have an input data word D1, D2, D3, and so on, and you have a transducer which is supposed to implement the transaction F. The question is, does the transducer need to remember D1 or not? That's the question. So it turns out that a similar question has already been answered for automata as opposed to transducers that I'm considering here. So in fact, there are two previous papers which answer this question. I have borrowed a lot of details from the second paper here. So let me explain what the second paper says about remembering data values. So instead of the transaction that we have, let's consider a language of data words. Okay, so this language consists of exactly those data words where the first and the last data values are equal. So if the first and last data values are equal, then the data word is in the language. Otherwise, the data word is not in the language. Now, suppose you have an automaton which reads data words and checks whether the data word is in the language or not. The corresponding question now is, does this automaton need to remember the first data value 1? So this paper here gives a definition which says that yes, you need to remember 1, and the definition works like this. Well, to decide whether you need to remember 1 or not, what you do is take this 1 and replace it by something else. Let's say 5. I've taken 5 because it doesn't occur in the rest of the word. That is somewhat important, but I'm not getting into the details of why exactly that is important. For now, let me just say that replace 1 by something else, let's say 5, and see whether this replacement makes a difference to the rest of the data word. Okay, so if you have 1 as in the original data word, then the data word is in the language. But if you replace the first occurrence of 1 by something else, right, then the resulting data word is not in the language. So replacing 1 by something else makes a difference. And hence, you need to remember that it is 1 that you have seen and not something else. Okay. So this is what was given in the earlier paper. Now, if we try to adapt it to the so before, let's try to apply this definition to the second data value. Okay. The second data value is 8. Let's replace it by something else, 7. It is not making any difference. 1831 is in the language and 1731 is also in the language. So it's not making any difference. So 8 might have been anything else and it wouldn't have mattered. So we don't need to bother remembering whether what we saw is 8 or something else. We can just forget it. Okay, this is the definition from the second paper for languages of data words. Now let's try to apply the same thing to transductions over data words. Now to compute this transaction on 1831, does our transducer need to remember 1? Well, if we try to apply this definition, replace 1 by something else. Okay, so if you have 1831, the output is 1831. If you have 5831, the output is the reverse 1385. So it does make a difference. So yes, we need to remember 1. Okay, but the story doesn't quite end here, because let's see what happens with the second data value. We have 8. Okay, if we replace 8 by 7, the output again changes. If the input is 1831, the output is 1831. If the input is 1731, the output is 1731. So replacing 8 by something else is making a difference. Now, does this mean that we need to remember 8 as well? If you think about it, we should not need to remember, a transducer should not need to remember 8. It's the second data value which has nothing to do with the definition of the transaction. All the transaction says is look at the first and the last data value. If they're equal, do something, otherwise do something else. So the second data value should be forgettable. Okay, so there is something that is not considered in this definition. And what is not considered in this definition is the fact that what we need to check is whether the replacement makes a difference to the rest of the data word. Okay, so here what we need to check is we are replacing 8 by 7, and what we need to check is whether the replacement makes a difference to the way the rest of the data word 3-1 is transformed. Okay, so for this what we need to know is some kind of a relation between which part of the output comes from which part of the input. Okay. So here, for example, this 3-1 in the output is coming from this 3-1 in the input. Okay, so we should have some kind of a relation between the positions of the output and the positions of the input. And that is exactly what is done in this work on transducers with origin information. And in fact, conveniently in that work, there is also a definition of something called a factored output, which lets us ignore certain parts of the output. Okay. So for example, we have read 1/8 so far. Let's say the transducer has read 1/8 so far, and transducer wants to decide whether 8 should be remembered or not. So 1/8 has already been read. So to check whether 8 should be remembered, the transducer needs to check whether what is coming, okay, the suffix 3-1 that is coming, will it be affected or not? So the transducer wants to ignore the part of the output that comes from the part of the input 1/8. So the factored output defined in this work says that, well, if your output, if for the input 1831, the output is 1831, in the output, just ignore the part that comes from 1/8. Okay, so replace that by star. Okay, so the yeah.
Sorry, if you can try to a bit to wrap up.
Yes. Yeah, I just need to
allow for one question.
Yeah.
Thanks.
Right. So the factored output just says that we'll just replace the 1/8 by star because you don't care about what it is. Then the factored output becomes star 3-1. And you can see that for 1731 as well, the factored output is star 3-1. So replacing 8 by 7 is not making a difference. So you can safely forget 8. Okay. And just to make a sanity check, you can see that if you replace 1 by 5, it still make a difference. If you replace 1, the 1 by 5, the output changes from star 831 to 138 star. So 1 does need to be remembered. Okay. So this is how I capture the notion of what data values need to be remembered. Now I'll skip a lot of details and just mention that based on this notion of what data values need to be remembered, I define an equivalence relation on data words. Okay, based on how many data words how many data values need to be remembered in each of the data words. And if they are same and if they occur in the same order, there is a precise definition of what is an order. I won't get into details here. So based on those, I define an equivalence relation on data words. And the main result is kind of a counterpart of the classic Mahil-Nerot theorem for regular languages over finite alphabet. The main result is of the form: a transaction can be implemented by SSRT if and only if the equivalence relation that I defined here has finite index, and there are a few more conditions that are much simpler to state, but again, due to lack of time, I won't get into the details here. But it turns out that many of the techniques that are available for finite alphabets are not available here. For example, one thing that is absent is there are no known equivalent two-way transducer models. So this makes the proof of the main result much more difficult. but there are some workarounds that I have implemented. You can look at the paper for details. So for future work, so as I just mentioned, we can look at other models, for example. So one thing that has been pointed out to me by the program committee is this single-use registers, which has some nice closure properties. Another thing that is missing in the paper is canonical transducer. Usually with this Mahil-Nerod kind of theorem, you expect to come up with a canonical machine that implements a given transaction, but here that is not yet here. And another area to be explored is whether the techniques of nominal automata can be used for analyzing these transducers. Thank you.
Canonical transducer usually. Thank you. Thank you, Praveen. Are there any questions from the audience?
This is me, Amal. Hi, Praveen. Is there a MSO definition for these transactions? Because
no, I don't know of any MSO transaction for these kind of transactions. One thing that I am aware is a logical characterization for transactions, but where the data values do not play a role in decision making. They are just kind of piggybacking on the finite alphabet. All the decision making is done only based on the finite alphabet. But if there are some data values in the output, you can kind of copy it to the output. So for those kind of transactions, there are some MSO characterizations known. But for these streaming transducers over data works, I'm not aware of any logical characterization.
Okay, thank you.
Other questions? So I have a short one. So can you compute the minimal number of registers with your characterization?
No, right now I don't have any result on that, and I think that with the current result it is not possible because I think there is some little bit of redundancy in the equivalence relation that I have defined. There are two types of memorable data values that I have defined, and I think there is some redundancy in these two types. I think these can be kind of reduced to just a single type. And if we do that, then I think we can come up with some kind of a minimum number of registers. But as of now, I don't have any result, but I think the answer is no.
Thank you. Yeah, so we are beyond the time schedule, so no time, unfortunately, for other questions. But you can still stay here. So let us thank again to all speakers of the session and all of those who are here. Hello to everybody that I see or I don't see. Hello, Paul. Hello, Sven. Hello, Amal. Hello, everybody. So you can stay still here and in the session and ask some questions if you want. Ask the author some questions. Yes.
Sorry, Anka, just one additional information for your question. I forgot to emphasize that this is actually a directed connected graph with cycles. Because I have a Leibniz assumption. So based on this, we get this lower bound. Sorry, I forgot to just emphasize this point.
No, I understood. Yeah.
Okay, thank you.
Thank you. So, thank you to everybody.
Thank you, everybody.
Thanks, Anka. We also have this gather space. So if people want to go, they can meet there and gather as well. I can paste the URL in the chat box. Just a second.
And just to say something final, so I hope that next time FSTTCS will be a real one. Because I think as everybody around hopes. So.
Yeah, so I've pasted the URL onto the chat box. Yeah, so you could use this as well. Thank you.
But do you plan for future FSTTCS to have also remote participation?
I think at this moment, nothing has been decided on the change of protocol. So we are hoping that next year. So if it happens next year, if there is a physical meeting, it will be in Goa. that's the place that we missed this time.
Okay,
Yeah.
thanks.
Now you are more in favor for a physical meeting, Anka, right?
No. I'm in favor of. I mean, I think physical meeting has obvious advantages, but also being able to participate remotely has also a lot of advantages. So to have the
Yeah,
best
sometimes
of worlds yes, please.
Yeah, some of our speakers probably don't want to travel for various reasons. So there could be genuine reasons why it might make sense to allow people to have remote presentations.
But it's
Perhaps
in
for
Goa.
a small number of people. Yeah.
Yeah.
The climate of beaches in Goa, I've heard, are
Exactly.
second only to those in Liverpool, and that is.
I think we are missing something in Goa, which is very sad. So I'm hoping next year it will all be physical, because the venue is again going to be Goa, right?
Yeah, but the only problem is that you won't get millions and millions of people vaccinated until next year. We were doing a small computation this morning with the kids, looking at how many people were vaccinated in UK and how much time it takes if you continue at the same speed. So
That's very easy. Currently, there are 0 people because there are only the first people who got the first of the 2 shots.
yes, but still more than 100,000, right?
I don't know. We only have something like 200,000 people to vaccinate at the moment. So the UK was the first people to was the first country in the West, at least, to start with vaccinations. But with these particular vaccines, we were the last to order them, and I think we got something like 400,000, which will then last for 200,000 people. It's a laughable small number. We just volunteered to be the guinea pigs.
But I think Americans are also not in a very, very good shape regarding the orders. Okay, so I think we follow the suggestion of Sunil, and if you want to go on Gather Town, so maybe there you can continue, and maybe the authors will be also around, and you can continue to ask them questions if you still have some. So let us close the session. Stay
Thanks,
safe.
Anka.
Bye.
Thank you.
Bye bye.
Thanks. Bye.
Bye bye.
Thanks, Anka. Thanks, Sunil.
Thanks.